Today we're going to look at how we can go about resolving more than two forces. This is everything we're doing today is really year 13 mechanics material. So I'm going to explain certain things that are new. So we'll look and see how we resolve more than two forces. And typically all the problems you're going to get on an exam are going to have more than two forces. Then we're going to look at what we call static equilibrium. That's when the resultant equals zero. That's when an object is not moving because all the forces are balanced in all directions. And we're looking at that static equilibrium on when a particle is held on a string or when a particle is held on an inclined plane. The vast majority of your exam questions are really on these two. And then we'll look at some past paper questions on these same topics just to show you how that works. So I have, I think, 3 or 4 different problems here that involve static equilibrium, or what we're doing here is to find the vertical component of these forces, and then the horizontal component of those forces, and then find the magnitude and direction. I'm going to do this first one, and then I'll get you to do some on your own, and then make sure that we understand. This is not difficult to do. So give me a second here. Right. Okay, so I'll get started here. Yes, I'm choosing a blue pen here. So what we're going to do here is first resolve our forces. I need to let some 2 people in, so. So what we need to do here is to first resolve vertically. So what I'm going to do here is we always write our forces like this. So we're resolving vertically like this. Resolving vertically, I start with the positive. So I'm going to say 10 sine 25, which is my first force here, plus 12 cos 40 degrees, which is up, and then I'm going to subtract 6 sine 65 minus 5. So these two are downward forces because the nearest vertical axis is this one. This one is already on the vertical axis, so these are negative, and these two are positive. So that's resolving it vertically. Then we're going to resolve horizontally. And then how we'll do that is I'm going to take the positive x-axis as positive. So this is 10 cos 25, which is this force here. And then we don't count any forces that are actually on the axis because they are neither horizontal. This is a purely vertical force, so there's no horizontal component. You can actually put it if you like. You can say plus 5 times the cosine of 90 degrees. The cosine of 90 degrees is 0, so this will just end up not changing, but you can put it in if you like. Minus, now these two are pointing left, so I'm going to make them negative, negative 12 sine 40. And this one here is negative 6 cos 65. Okay, so we'll go ahead and put these all on the calculator. To find the resultant and the direction, we're going to use the calculator as well. So let me put these in on the calculator. So I will get the vertical component first. Let me write it out here. And I'll just do it all on the calculator. As one shot. 10 sine 25 plus 12 cos 40. And I'm just writing them out exactly the way I wrote them out on the other side. Sine 65 minus 5. And I get my answer as 2.98. And you tend to use 2 decimal places. So this is 2.98. Photons. That's my answer. Then I'll do the same thing for the other one. And like I said, this is primarily year 13's material. So 10 cos 25, but it's important to be able to understand how to do this in order to understand what we're doing next. So 12 sine 40, this was minus because those are all pointing to the left, minus 6 cos 65. And the 5 doesn't count, but you can actually add it if you want. Plus 5 cos 90, which is going to be 0 anyway. So answer is minus 1.19. So we'll put that in here. So this equals minus 1.19. So if I draw it the way it looks, this is the horizontal component, which is 2.98. And the vertical component is downwards. I'm sorry, it's the other way around. I did the vertical first, so I'll do the horizontal one here first. So the horizontal one is this way, minus 1.19, and the vertical one is up, which is 2.98. So my resultant looks something like this. Now, of course, you can use Pythagoras theorem or just use the calculator. When you use the calculator, you put in the pole, then the horizontal first, and then the vertical. There's a reason we put the horizontal in, because we want the angle with the positive x-axis. So let's put that in exactly the way it is. Yes, Elsie, you had a question.
Yeah, you say when like a force is lying on the axis, like the one of 5 newtons,
Yes.
when you're doing the horizontal forces, you don't count it in, right?
Yes, it's purely vertical. You can actually make it a horizontal force, but it's going to equal. So like if I said 5 cos 90, it'll just be 0.
So
Just
if
telling
it
you.
was if it was lying like on the x-axis, would it still also be 0?
No, if it's on the x-axis, and I'll show you an example in the next one. If it's on the x-axis, then you take it as it is for the horizontal, but for the vertical, it means nothing. So if it's lying on the vertical y-axis, then you count it as the vertical and not the horizontal. If it's lying on the horizontal x-axis, horizontally, then it counts as horizontal and nothing as vertical. But everything else in between has to have both.
Okay.
Yeah. So I'm going to use the calculator here and use the pole function here. So shift plus. I put in the horizontal one first, which was minus 1.19, and then a comma. Mine is a semicolon, but yours is a comma. And then 2.98, which was my vertical component. And now enter, and I get 3.21. newtons as my resultant, and the angle with the positive x-axis is 112 degrees. So I'll write this as my resultant, and of course you can get this using trigonometry also, is 3.21, and my theta, which we always count from the 3 o'clock position, the positive x-axis, is 112 degrees. Now, if I was going to draw this out, it would look something like this. This is my force, my resultant force, which is now 3.21 newtons. And this angle here is 112 degrees. And that's the result. And you can see that that's the reason, because here we had minus 1.19, and then we went up 2.98, and that was our result as the hypotenuse. And basically that's what we're doing with more than. So I'm going to get you to do this one, and then I will show you. Notice here we have two forces. One of them is lying on the y-axis, which is 2 newtons, so there will be no horizontal component. And one of them is lying on the x-axis, 1 newton, which means there's no vertical component, but the other two will have both. So first find the horizontal, and then find the vertical, and then find the resultant and the angle as well. I'll give you 5 minutes maybe. My advice here is always just be careful when you're entering the degrees. It's very easy to put in a number and, and always understand why you're doing cos and sine. So if I am taking this and turning it this way, I have passed through 45 degrees, so this one will be cos 45. If I take it and turn it the other way, then it becomes sine 45. Same thing here. This here, when I turn it up here, it will be cos 60. When I turn it down here to this vertical, it will be sine 60. So moving away from the angle is always sine. Moving through the angle is always cosine. All right, so I'll give you 5 minutes to do this, and then we'll come in and solve it. And when you find your components, make them to 2 decimal places. Okay, let's have a go at this one. I will start with the horizontal. And typically on your mark scheme, sometimes you'll just find them drawing an arrow like this, indicating that it's horizontal. So horizontal, we will start with the positive x-axis. Now I can say 1 times cos 45, or I'll just say cos 45, because multiplying it by 1 is not going to change anything. I'm referring to this particular one here, so I am turning it this way. So that's cos 1 times cos 45, or cos 45. This one here has no horizontal element, so I'm going to leave it out. The only other horizontal ones are this one, and they are pointing in the negative direction. So I'm going to subtract 1 Newton and also subtract 3 cos 60 and get that answer here. Now for the vertical one, this one here has no vertical component, so we'll not include it. So it will be this one and that one, which will be included. And so I'll start with the 1 Newton. So this is sine 45, because it's 1 times sine 45, and I'm moving away from this 45-degree angle, plus 2. So both of those are positive. And then I'm subtracting 3 sine 60. And I get that answer as well. Now, if you've done this correctly, the vertical component should be 0.11 newtons. And this one here should be minus 1.79 newtons when you do that. So I'm going to do the horizontal one just very quickly on the calculator just to verify that. So what we had was cos 45. And by the way, one thing I also want to remember is that whenever you do these kinds of things, make sure you're in degree mode on your calculator. We never use radians for this one, and you haven't learned radians anyway because that's year 13 material, but we'll always use degrees in this. Minus 3 times the cosine of 60. It'll give you so minus 1.79, which is what I got. And I did the other one, which was sine 45 plus 2 minus 3 sine 60. And you get 0.11 to 2 decimal places. Okay, now what we'll do is find the resultant. So we'll do pole. We put in the horizontal first. So this is minus 1.79. And then a comma. And then the 0.11. And we'll get 1.79 as our resultant, and the degree is very close to 180 degrees, so 1.76. So what this means really is we have something that looks like this. So the horizontal was minus 1.779. The vertical one is extremely small. And so this line here, should have drawn it as a straight line, but this resultant here is very, very close to the horizontal one. So it's also 1.79. And that this angle here with the x-axis is very, very close to 180 degrees. So essentially the resultant and the horizontal are almost on top of one another. The only reason this is negative is because this one has a sense of direction. This one, we don't usually give it as negative because it's the resultant and it's from Pythagoras theorem. It's the angle that determines on which side it is. Okay. Now, I had done this one. It's I'm going to write it out and give you the answer. But what I want you to do is to understand why I'm making each step. This is a case where we have 5 different forces. This is overkill. You'll never really have 5 different forces, but I just created it just so that you can understand. Now, all of these are not on the axis, so all of them are going to have 2 parts. So if I write this out very quickly, I'll do the horizontal one first. The horizontal one, I'll start here. So I'll start by saying 3 cos 30 plus 2 sine 20 plus, and I'm going to take this one down here, 6 sine 15, because this one has the closest axis to the positive one, minus the other 2, which is 8 cos 25 and 50 cos 40. Okay, so just make sure you understand why we're doing that. And then, of course, you can find the answer. Once you've done these and you got them correctly, then the rest is not really that difficult. So the vertical one, I'm going to say 3 sine 30 plus 2 cos 20 plus 8 sine 25 minus 5 sine 40 minus 6 cos 15. And that's how you get both the vertical and the horizontal. If you did this correctly, this would be 1.01 newtons. Actually, it's the other way around. So this one is, and this one here is minus 6.25. The resultant turns out to be 6.33 newtons. And the angle theta with the x-axis is 171 degrees. So this one is also very, very close to this axis here, because you're taking 171 degrees here, and it's almost this way. And you can tell that it is because these forces here that are on the negative side here are much larger than the ones that we have here. So together these add up to 11, but these ones here are 13. And so you'll see there's a tendency for it to be on the left, pointing to the left because of that. Any questions on this? On why this has been set up like this, and understanding how we get the components and then getting the resultant and getting the angle? Any questions? No? Okay. Now let's look at, this is now, like I said, purely year 13 material. We're looking at what we call static particles. Now, a static particle is a particle, when we say a particle is in static equilibrium, that means it's at rest and the force that's acting on it is 0. So all the forces, all the horizontal components are 0. All the vertical components are also 0. So that object is not moving. Now, this becomes important because you sometimes need that information in order to find unknown forces. So to solve problems in statics, you usually draw a diagram in the same way we've drawn those diagrams, clearly showing all those forces that are acting on the particle. Usually they will give it to you to do that. You will resolve all those forces into horizontal and vertical components. Or if the particle is on an inclined plane, you resolve them into components that are parallel and perpendicular to the plane. So what we're doing is, if I have an object that's on an inclined plane, like this, and I have a box maybe that's on that plane, then when I'm resolving my components, I resolve parallel to the plane. So parallel to the plane, and also perpendicular to the plane like this. Now notice this is not X and Y, but that's the best way to do that. And essentially all your questions on inclined planes will be set up like that, so that, and they will almost always give you an angle here, theta, which will help you to decide how you're going to tilt this. But it's not very difficult, just as long as you understand on an inclined plane, we're doing it parallel and perpendicular to the surface of that inclined plane. Now we set the sum of our components in each direction to 0 and then use those equations to find unknown forces. So essentially we're doing simultaneous equations here. But sometimes you have to get very creative, and it comes with practice. Now there's another concept that I would not advise you to use. Your teacher may decide to teach it to you. It's called Lamy's theorem. Lamy's theorem is taking all these forces and now making them triangles. The problem with Lamy's theorem is the angles you get here are not the angles that you're using inside the theorem. And I'll show you using this example here. I suggest that you solve it using the way we have essentially done horizontal and vertical components. So here we have a diagram that's a particle under equilibrium. So the particle is here. By resolving horizontally and vertical, find the magnitudes of the force P and Q. So there's a force P here, and there's a force Q here, and there's another force 4 newtons. Now this particle is not moving, it's at rest, so all the forces horizontally and all the forces vertically must balance. So let's look at method 1. That's the method we are familiar with. When you see the R and the arrow horizontal, that means we're resolving horizontally. So resolving horizontally, we say P cos 30. So that's this one here and here, minus 4 cos 45. So this is the force 4. And we've also turned it through 45 degrees, but it's in the opposite direction. So we write it as minus, must equal 0. So essentially, this is the only horizontal component positive. This is the only one negative. This one doesn't count. Now here we're resolving vertically. And so we'll take this P and take it up here, and that becomes P sine 30. Then we'll take this 4 and take it up here, and that becomes 4 sine 45. But P is vertically downwards in the negative direction, so we subtract P, and we say that's all equal to 0. What some people do, and there's nothing wrong with that, is to recognize also you can write it like this. I'll write it this way. It means exactly the same thing. P cos 30 is equal to 4 cos 45. And the reason why that is easier to see is that this is positive, that one is negative, so they equal each other, and the result is 0. Same thing here, that this one up here plus this one up here are going to equal this one down here. So you would have written that as 4 sine 45 plus P sine 30 is equal to Q. You can also do that. It's the same thing, really. Now, what we do here, as much as possible, we try and use one of these equations that has only one variable in it. So this first one here only has P in it. So what they have done, once they've done it here, is to now come up here and then divide both sides by cos 30. So that's why I suggest that instead of writing this, you can essentially go directly to this, because you know at the end you're going to divide this side by cos 30 and this one by cos 30. That's what they've done here. So they find the value of P. Now, once they find the value of P, they can substitute it in here. And now the only unknown is Q. So once you know P, then you know all the others, because you can put them in a calculator and you get Q. Now, once you have set it up like this rather than like this, then all I would have done is 4 sine 45 plus P, which I got here, sine 30 equals Q, and you get the answer for Q. Now, the other method I was telling you about is Lamy's method, and I will make a separate video for it, but it is never advisable to do this, because you'll notice that all the angles they have in here in Lamy's that are here in Lamy's triangle did not exist over here. So there's 45 degrees and that one is here, but this 30 becomes a 60, and now there's also 75 degrees. So it's a messy thing. Unless you're absolutely sure you know what you're doing, it's easier to stick with this method and get the answer. And actually, this one turns out to be shorter. Yes, Hannah.
So can they ask us, like in a question, specifically to use the Lami's method?
No, they won't. They will want you to learn it. And by the way, Lami's method only works when there are three forces. If there are two, it doesn't work. If there are four, it doesn't work. So you can only, because Lami's theorem, eventually you're required to make a triangle. So you have to have three forces. In this case, there's P, there's Q, and there's the force 4. So you can only use it when there are three forces. But this method can work for any number of forces. You'll notice the last example we had 5 forces, I think. This method works for any number of forces, whether they're 2 or 4 or 5. So Lami's theorem only works for 3, but they will never ask you. I have never ever seen a question where they ask you use Lami's theorem, because they recognize it's not, it's very easy to make a mistake if you get the angles incorrect. Because really, I'm going to explain what they're doing, and then you will understand here. Is if we go back to, with Lami's theorem, what we're doing here is we're taking this force here and drawing it like this. So that's P. Then we now take this force here, that's Q, and what we do with it is to move it here, like that. Okay? Then we take this force here, which is 4, and now take it and move it so that we close the triangle. And that's how we do that. Now, the trick becomes, what was the angle between P and Q? If this is P, this is Q, and this is 4. Okay, I can figure out that this angle here is probably the same angle here, because Q is vertical. And it's actually this angle here that we are looking at, the vertical force. This is 45 degrees. It's this angle here that we are taking and saying it's the same as this one. So that's why this one down here became 45 degrees. That's easy to understand here. Now, why is this one 60? Because this angle here is 30. This one here is 90 degrees. So this one here has to be 60 degrees. That's why this is 60. Now this is 60, this is 45, and you'll now get this one by subtraction. 60 plus 45 is 105. And this one has to now be 75 degrees in order to make 180 degrees. But you see, you have to be very careful that you have moved them correctly and you have understood where the angles are. So yes, it's possible to do it. I'm not going to say you can't get the answer that way, but it's very easy to make a mistake. And once you get the degrees wrong, then the whole question will be wrong. Yeah. Okay, let's look at another question here on an inclined plane. Here we have 4 forces. Now, because we have 4 forces, Lami's theorem is not possible here. So we have to go back to the resolving horizontally and vertically. But because we have an inclined plane, we always resolve horizontal, parallel to the plane, and also at right angles to the plane. So this one, you can essentially take it as our vertical, and this one as our horizontal, if you like. That's entirely up to you. So let's look and see how they did this, and follow it carefully. I'll rub this off so that it doesn't confuse us. Okay, they're resolving, when you see this, they're resolving parallel to the plane. So they're assuming that it's going up like this, so they're resolving parallel to the plane. They've turned this force this way, parallel, So this is P cos alpha, which is here. That's the only force going upwards here. This one is perpendicular to the plane, so we're not going to deal with it. But this 8 is directly opposite this P cos alpha, so that's why we subtract 8. Now, the force here for 5, the nearest, because now our axes look different. Our axes are actually this axis here and this axis here. This force, the nearest horizontal, is actually this way. So this now becomes, but remember, we have to figure out that this here is 60 degrees. Now, you can write this as 5 cos 60 or as 5 sine 30. That's up to you. It's the same thing. Here they've done it as sine 30. And there's a reason why they do that. Whenever we're looking at an inclined plane, and this is a very common question, and we have a particle that's on an inclined plane. That particle has a weight which goes straight down, which we call mg. Now we resolve it perpendicular to the plane, and that movement to the right is always mg cos theta. And theta is this angle that is here. And this one here, which is parallel to the plane, becomes mg sine theta. Now there's a reason for that. This angle here is 90 minus theta. So if we pass through it, it's the same as writing mg cos 90 minus theta when we're going this way. Now, cos 90 minus theta is the same as mg sine theta. And so we just shorted it and say, okay, it's mg sine theta. Just remember that whenever we're doing an inclined plane and we're looking at the weight of an object that's on an inclined plane, if we turn it to the left, it becomes mg sine theta. And if we turn it to the right so that it's perpendicular to the plane, it becomes mg cos theta. So what some people do is remember parallel is mg sine theta and perpendicular is mg cos theta. So that's why this is mg. That's why this here is 5 sine theta. 5 sine 30, because they've taken this and turned it this way. So this 5 sine 30 and 8 newtons are opposite to P cos alpha. So that's our first equation here. My suggestion is always to write it like this. I didn't understand why they do it this way. It's just to notice that this one, which is pointing up here, is opposed by all those that are pointing downwards. You can always to rearrange the equation like that. Now let's do it perpendicular to the plane. Perpendicular to the plane, I am going to take this one and turn it up here. So I'm going to get something that goes up here, and this is P sine alpha. So P sine alpha plus 2 is going to equal this one here, which is 5 newtons. It's opposite. 5 cos 30. This one down here, because I've turned this and this is 30 degrees. This turning to the right is always the same as the angle that's here. They're always the same. Simply because this one here is 60 degrees. So to make a 90-degree angle, this one has to be 30. So you just remember that it's always the same as the angle of the incline. So that's why we have this here. P sine alpha, which is this one up here, plus 2, which is also pointing upwards, minus 5 cos 30, which is this one downwards, should equal 0. And of course, you can rearrange this and take all the numbers on the right side, and now we get P sine 30. Now, whenever we get something like this, we will take this expression here and divide it by this one and get tan alpha. So you divide equation 2 by equation 1. So tan alpha will be this expression divided by that one. and we solve them on the calculator, and we get the tangent of alpha. And then we'll do tan inverse and find out what alpha is in degrees. So we now know that this angle here is 12.5 degrees because we found the tangent here and plugged it tan inverse. Now, once we know what that is, once we know what alpha is, then solving all these values for, you can pick any equation you want, any one of the two. Equation 1 here or equation 2 to find P. That's entirely up to you. Here they chose equation 1 and they substituted it as P sine 12.5 equals 5. Actually, they said equation 1 here, but it's actually equation 2 they used here. There's a typo here. P sine alpha is equal to 5 cos 30 minus 2. So they used equation 2. And they know everything else except P, and then you can find the value of P. And what you do sometimes is to take the value of P you've got here and put it back into the other equation you didn't use to make sure that it's still true. Once you found that it's true, then you know you have done it correctly. Any questions on this? We're going to get a chance to look at several questions on inclined planes. Yes, Hannah, go ahead.
Yes, sir. Could you please explain again how you got the second equation?
This one here.
Yes, please.
Okay, let's take these off here. The second equation is now perpendicular to the plane. Now what we're doing is, remember when I was doing those other questions on the other side, we had axes that were X and Y like this. Now what we're doing is we're taking these and turning them slightly this way. So what we have now is something that looks like this. Nothing changes. It's now we have just turned them slightly. So now that turning, because this is 30 degrees, the turning that I've done here is also 30 degrees. So I've turned the axis 30 degrees, but this is still horizontal and this one is still vertical. So what we do here is, now what I'm going to do is, I know that my axes are here, this one here, and this is another axis here. So if I am doing this vertically, because this one here is now the vertical one, I'm going to take this P and turn it this way. And this one is going to become P. It's going to lie in the same place as this 2. I just didn't want to draw it on top of it. This is P sine alpha, because I have moved away from this alpha degree. Now this one here, this angle here is always the same as this angle here. So this one here is 30 degrees. So if I turn this 5 newtons, I'm going to get something that looks like this. 5 cos 30 degrees. Like that. Now, these two are pointing up, so I'm going to add them together. And I'm going to subtract this one. Now, because this particle is not moving up or down, that means what I have added up here at the top should be the same as what I have down here. And that's what we're doing here. So P sine alpha, which is this one here, plus 2, which is this one here, should equal, and that's what they've written here, should equal 5 cos 30, which is this one. And that's why when we take the 2 that we have added and subtract 5 cos 30, we get 0. Now, what they've done is they've rewritten this so that P is by itself and all the other numbers on the other side. So all we have done is take this 5 cos 30, take it to the right side here, and then take this plus 2 and subtract it. So that's what we have here on the right side, and P sine alpha. Now, once we have P cos alpha and everything else, and P sine alpha and everything else, we now take this equation here and divide it by this one. So P sine alpha divided by P cos alpha will give us tan alpha, because the P's will cancel. And once we have tan alpha and you find the degree, then you can go back to any one of these two equations. It doesn't matter which one you choose. And I think they used this one. They found alpha here. So now the only thing they don't know is P, and you can now find the answer for P. Let me do an example on the next page and you will see. I'm going to try and find one on an inclined plane here. So let's pick an easy one first. I'll do A and B. So let me cut it out. Okay, here, and we always write it like this, that we are, I'm going to first resolve parallel to the plane. Now, parallel to the plane means I'm doing this. Now, Q is already parallel, so I'm going, and it's we usually take going up as positive. So it doesn't matter whether you're going up on the inclined plane or you're going, so this is considered positive, and this is considered positive. So Q, I'm taking Q as positive. Now, I don't have any component of P because P is already on the perpendicular axis. So this is not going to count for parallel. But this one is going to, because this angle here is 60 degrees. That means if I turn it like this angle here is 30 degrees. And remember, we said this angle is always the same as this one. So this force becomes 5 cos 30. Now, that's here. Now, when I take this one and turn it and it becomes here, this becomes 5 sine 30 or cos 60, whichever one you want. I've chosen sine 30 because I'm moving away from this angle. So I'm going to say Q is equal to 5 sine 30 because that's the only other force that's opposing it. Now perpendicular. Now this one I think is an easy example to start with. So perpendicular, I'm going to say P is equal to 5 cos 30 because this one here is opposed by this one here, and this one here is opposed by that one here. And this particle is not moving, so they must be equal. Now, if you remember, sine 30 is actually a half, so 5 times a half will give me 2.5. Cos 30 is root 3 over 2, so this is 5 times root 3 over 2. I take it they're all newtons, so those are our answers, and that's as simple as it is. That one is a very simple example. Here we only had 3 forces, and one of those forces was already perpendicular, so we didn't count it. The other force was already parallel, so it was nothing to do with perpendicular. Now it's not always that easy. This one is the same thing. Actually, there's really no difference between A and B. The only difference are the numbers, but they look exactly the same. P is on the perpendicular, Q is on the parallel. 10, this will become, this force here and this force here will become functions of 10. So this one is 10 cos 45, because remember this is 45 degrees also, and this will become 10 sine 45. So Q is 10 sine 45, P is 10 cos 45. Now 10 sine 45 and 10 cos 45 are exactly the same thing. So P and Q are equal the same thing. Now let's look at the version C here. Actually, I'm going to look at D, and then we'll look at C, because C is slightly more complicated. Okay, now, again, we want to do parallel to the plane and perpendicular to the plane. So I always tend to start with parallel. So we usually write it like this, that it's parallel to the plane. Let's see what we have here. This is going to be 8 cos 45. 8 cos 45. Here, because I've turned this one through 45 degrees, so I'm going to say 8 cos 45. Do I have any other horizontal ones? Yes, I have Q, which is in the opposite direction. Now, even this 10 has to be turned this way. And now it becomes 10 sine 30. Remember, this is 30 degrees here because it's the same as the one here. And I'm turning away from it. So this is now minus 10 sine 30 degrees. So whatever that answer comes is now my horizontal component. Now, I'm going to take this equation and say, I want to find Q. So 8 cos 45 minus 10 sine 30 is going to equal, because all of this should equal 0. I'm going to add Q to both sides, so this is going to equal Q. This is my equation that will help me find Q. Because if I know that Q plus this equals this, then what I'm going to do is take this minus this one, and now I have Q left, and that's what I have here. So that's my answer for Q. Let's find an equation for P. I'll take this off here. Are we okay so far on this? We've understood what we're doing here?
Yeah.
Okay, let's now do the perpendicular one, which is like this usually. Perpendicular to the plane like that. Now, this force here, this 8 is going to go up here. So that would be 8 sine 45. Because I'm moving away from that 45 angle. P is already on the plane. Q doesn't count because it's already on the x-axis, so that one has no vertical component. But this one here is 10 cos 30 because I've moved it through 30 degrees. So let's write R. So I'm going to say 8 sine 45 plus P, because those are both positive, minus 10 cos 30 should equal 0 because they're all equal. The ones going up are always equal to the ones going down when this particle is static, it's not moving. So how do I rearrange this equation to find P? I'm going to take all of these and take them to the right side. So I'm going to say P is equal to 10 cos 30 minus 8 sine 45. Now I have an equation for P and I have one for Q. I'm going to type them in the calculator. I'll do the first one and then the other one. Let's do the one for Q. And you just put them in as they are. So the one for Q was 8 cos 45 minus 10 sine 30. Now, this one here is negative because Q is on the negative x-axis, so that's okay. So let's get our answer here. So 0.66 newtons. And you can take the answer just as it is. The sign is not important. So Q equals 0.66 newtons. And for P, I'm just going to put it in on my calculator here the way we've done it. So 10 cos 30 minus 8 sine 45. I get my decimal as exactly 3 newtons. And those are your two answers for P and Q. Now, the simple way to check is to take this answer here and put it back in here and see if you put them in and get 0. So I'm going to take this 0.66, put it in. Sometimes you'll get an answer, but it will be very, very close to 0. But as long as you can see that. Actually, let's do P because P is a nice round number. So if I go back to my calculator here and I put in exactly the equation, but the value for P that I have. So I'll say 8 sine 45 plus 3, because P is 3, minus 10 cos 30. I should get an answer that's very close to 0. And it is very, very small. So that shows you have done it correctly. Let's look at this example C here. It's a little more complicated, but as long as you follow the procedure carefully, we have 4 forces here. Okay, before we begin, this is going to test your geometry. What is this angle here? Do you know what that angle is here? Does anyone know what that angle is? You obviously learned it in IGCSE. Remember when you did Z angles? And we said this angle here is the same as this one, as long as these two are parallel. So what we have here is for me to turn this force, this 2, and make it like this, I have to turn it through 60 degrees. Because this angle here is 60 degrees because this one here is 60. Okay, once we know that, then it becomes easy. And that's what these questions do, is they don't tell you what the angle is, but you sort of have to figure out that you're looking for Z angles. So let's resolve parallel to the plane like this. Q is already there and it's on the axis, so we'll say that's positive Q. This 2 cos 60 is also pushing up. So we'll write this as plus 2 cos 60, because this force is, this 2, when I turn it, it's actually pointing upwards in the same direction as Q. Okay, which ones are my downward forces? The only other downward force I have is this 6, which I am now taking this one and turning it like this. But remember, this angle is 60 degrees also. So I'm turning this one 30 degrees. So I'm going to write it as minus 6 sine 60. Because I'm turning away from the 60 degrees, but it's actually pointing in the opposite direction of Q and the 2 cos 60. So this now all equals 0, because those are the only forces. There's only one downward force, which is this one, which was turned here. This force here and this one here, once we turn them, they're actually pushing up. So that's why we add these two together and subtract that one and say equals 0. Let's do parallel, perpendicular to the plane. And find P. Now, yes, Michelle.
Can you
Michelle?
please explain how you get the 6 sine 60?
If we look at this force here, it's pointing downward. I'm going to turn it this way so that it's perpendicular. And I'm also going to turn it parallel to the plane. Now, if I draw a line here, this is pointing straight down. This is 90 degrees. This here is 30 degrees. And because this is a right angle, this one here is 60. Now, when I take this force, which is 6, and I turn it to this one here, I've moved away from this 60-degree angle. So this becomes, this force here is now 6 sine 60. Because I moved away from the 60 degrees that was here.
Okay, thank you.
And then, of course, this one will become 6 cos 60 because I have passed through the 60 degrees when I did it. Okay, so now resolving perpendicular to the plane, the Q has nothing to do with this. Q is already on the axis, so there's nothing about Q. So I'm going to say this is P. P is positive. And it's pointing upwards. Now, this one here I said was 6 cos 60, but it's pointing in the opposite direction of P. So I'm going to say minus 6 cos 60. Now, the tricky one is the 2. If I take this 2, I said this angle here was 60 degrees. When I turned it and it faced up like this, I said this became 2 cos 60. When I turn it and it faces downwards like this, I'm moving away from that 60-degree angle. So this one here becomes 2 sine 60, but it's pointing downwards. So this one is minus 2 sine 60. So always remember that these ones which are at an angle, you want to make sure you turn the force so that this one, when I finish, this 2 has to have only 2 parts. One which is parallel to the plane and one which is perpendicular to the plane. Those are the only components I need. Now, because this was a 60-degree angle and this one is a 30-degree angle here, because together they make 90, this one now becomes 2 cos 60. And you can write this as 2 cos 30 if you want, or you can write it also equal as 2 sine 60. Whichever one you choose, they're both exactly the same thing. I tend to choose the sine because I know that I've moved away from this 60-degree angle that was here. Now we all know that this equals 0. So I'm going to say P is equal to 6 cos 60 plus 2 sine 60. Whatever that answer is, will give you P. And let's also get one for Q here. Q is going to equal 6 sine 60 minus 2 cos 60. Because all we're doing is taking everything to the right side to find. So let's find P and let's find Q on the calculator. I'll do them on the calculator off here because I'm sure you all know how to do that. So 6 cos 60 plus 2 sine 60. When I enter those together, it gives me 3 plus root 3. I want to get the decimal, so that's 4.73 newtons. That's the value for P. Let's get the one for Q. So 6 sine 60 minus 2 cos 60. I get 4.20. So those are our 2 answers. Now we're going to plug them in here to check that they are correct. So I'm going to plug it into this equation here. And it has to be because I've just done it on the calculator. All I did was to rearrange the terms, which were numbers. So it doesn't really make sense to put it back in because it's like you're testing the calculator itself, and yet you have just used the calculator. If I take this value for P and put it back in here, it's still going to give me 0, but let's try it anyway. So what we're doing on the calculator here is 4.73 minus 6 cos 60 minus 2 sin 60, and our answer should be very close to 0. So let's go ahead and do that. So 4.73 minus 6 cos 60 minus 2 sin 60. And you can see it's also another very small number, slightly negative, but very small. Okay, so that's basically what we're doing on an inclined plane. In the time we have left, I'm just going to show you the ones that we do on a string, which are slightly easier than an inclined plane. But you have to know both because in the exam, there will be one or the other. They like these questions a lot. So you will find that they appear every year. It's whether it's a string or an inclined plane that you have to learn how to. Strings are slightly easier. So I'm going to go to a string question here. This is a simple one, but you can see that they do carry a lot of marks. This one here is 7 marks. And in fact, I never understood how this could actually be 7 marks when doing this is not difficult at all. It will take you less than 3 minutes even to do this, but you get a lot of marks here. So here we have, this was the June 2015 paper. And this was the question here. This is a particle that has a mass of 2 kilograms. So this is the particle here. It's suspended from a horizontal ceiling here by 2 strings, inextensible strings. So the strings don't stretch. This is the first string PR, and this is the second string QR. The particle hangs at point R in equilibrium, which means it's not moving left or right or up or down. It's just static with the strings in a vertical plane. So that means everything is in one plane. The string PR is inclined at 55 degrees to the horizontal and QR is at 35 degrees to the horizontal. Find the tension in the spring TPR, so the tension in this one and the tension in this one. Now, what we first do with these string questions is they will always give you a mass of the object. So we calculate the weight of that object. Now, the weight is always the mass times gravity. So we write this as 2g. The mass is 2. G is the value for gravity, as all of you who do physics will know. So the weight now here is 2g, pointing straight downwards. And for purposes of mechanics, G is always equal to 9.8 meters per second squared. That's actually given to you on the front page of the paper. So don't ever use another value of G other than 9.8. If they're going to ask you to use a different value, they will tell you in the question to use a different value. But sometimes in physics we use 9.81, but for mechanics in math, it's always 9.8. So this is G, 9.8. So the weight of this object is 2G. Now what we want is the tension in this string. Now the tension is always pulling upwards. So I'm going to call this T1, tension 1, and this one here I'm going to call it tension 2. Now what you have to do is to resolve both vertically and horizontally. So let's draw a line here. I'm going to draw a set of black lines here to make it X and Y plane. So first I'm going to begin by, you're really going to get simultaneous equations and use them to solve. So let's first resolve vertically. And you all know how to do this now. Now remember, if this angle here is 55, this angle here is also 55. And this angle here is 35, so this angle here is also 35. So if I'm resolving vertically, I'm going to say T1 sine 55, because I'm moving away from this 55 angle by going up like this. So this will become T1 sine 55. Then T2, same thing, it will go up. So this is T2 sine 35. So T1 sine 55 plus T2 sine 35 should equal, those are the only upward forces, should equal the weight of that object pulling downwards because it's not moving. So this is equal to 2G. Because 2G is the only downward force, the other tensions are upwards. Okay, so we've done that vertically. Now let's do horizontally. Now this object is not moving left or right. So I'm going to take this T1 force that is here and turn it this way horizontally. And then take the other one, which is T2, and turn it this way, which is horizontal. Now they must balance because the object is not moving left or right. So I'm going to say T1 cos 55, because I've turned it through 55 degrees, is going to equal T2 sine 35. Okay, now this equation, the second one we've got, is actually the one which is going to help us to solve this. So I want to make T1 the subject here. So I'm going to say T1 is the same as T2 sine 35 all divided by cos 55. Okay, so this is my expression for T1. Now I'm going to take this expression here for T2 and put it here. And now my equation will become, yes, Elsie.
So for T2, if you're going through the angle 35, is it cos or I?
Yes, it's cos, you're right. I did that incorrectly here. Yeah, so this is cos here. Yes, you're right. It's cos. Let's change that here as well. So this is also cos. You're right. Thank you. Because we passed through those both angles. Yes. So let us rewrite this first equation. And then we'll make T2 the subject. So we're going to say T2 cos 35 all divided by cos 55 times sine 55 plus T2 sine 35 is all equal to 2G. Okay, so let's make T2, factorize out T2. So it gets, you have to be very careful here as I'm going to put it in brackets like this. Okay, now we will divide everything on the right side by everything that's on the left side here in the square brackets. So T2 is going to equal 2 times 9.8, all divided by everything here. Cos 35 over cos 55 times sine 55 plus sine 35. And let's put that in the calculator as is. Now, take the liberty of writing it here, so let me just check it is. Now, oh yeah, what I did, you don't have to do it. Let me go back here and make it one slide. You'll understand why I've done this, just to make life a little easier. This here and this is actually tan 55. So I can write this as T2 equals 2 times 9.8 all divided by tan 55 times cos 35 plus sine 35. It looks a little simpler, but you will understand. It's the same thing. Sine 55 over cos 55 will be tan 55. Okay, let's go ahead and put this in the calculator. I first get my fraction. So 2 times 9.8 all divided by tan 55 multiplied by cos 35 plus sine 35. So we have an answer of 11.2 newtons. So that's T2. Okay, once you have T2, of course, getting T1 is not difficult because you already have a formula with T1 as the subject. So I'm going to go back in here. I'll just change the color so it's obvious. So here we're going to have, maybe I'll use a different color here. 11.2, which is T2, times the cosine of 35, all divided by the cosine of 55. And we'll get that answer. I'll do it off the screen since it's obviously much easier. So 11.2 times the cosine of 35, all divided by the cosine of 55. And I get 16. 16 newtons. So we have T1, which is 16, and we have T2, which is 11.5. So I'm going to show you the mark scheme here. And essentially that's what they've done here. So you can see that this is T1, which was 16, and T2 is actually 11.2. Now, I don't see where the 7 marks are here, but yes, I think you get 2 marks for setting this up this way. For us, this was T1, and this is T2. Then getting the second equation, also 2 marks. Then you can either eliminate them by getting a subject or substituting. Then you'd get that 1 mark and then 2 marks for the answers. And that's how you do that. That's how we do string problems. Now, this one is one of the most straightforward ones. But yes, I'm going to show you another one, and maybe that's where we will end. This is another string problem, which is also not difficult. Actually, I'm going to get you to try it. I'll just give you a hint here and say that they've given us the weight here. So it's not mass, it's already weight. So this one we know there's no G involved because it's already weight. So this is 24 newtons. You're going to have to find a vertical component here also, which will equal this 24. And you're going to have to find a horizontal component, which is equal to this Q. So try and find the value. And notice that these are, there are 6 marks. This is 3 marks here, and this is 3 marks here. So they carry a lot of marks, but they don't take that long to do. So give yourself, I'll give you 3 minutes or so just to do that, and then I will solve that one, and we will leave it there for today. Unless somebody has questions. Okay, so let's look at this one. Let's do the vertical one first. I'm going to say P sine 30 is equal to 24. And because of that, I can find P directly. Now, sine 30 is actually a half. Someone says 48 newtons. And that took less than a minute, but it's 3 marks, which is amazing. Now, horizontal. The value of Q, so I know that Q is equal to P cos 30. So Q is going to equal 48 times cos 30. Now cos 30 is root 3 over 2. So this gives me 24 root 3. I can find the answer on the calculator. I get 41.6, let's say. Okay, and that's it. Getting 6 marks in a very short space of time. Let's look at the mark scheme here. And that's it. Yeah. P is 48. I didn't even know where the marks were. 2 marks for setting the equation up, 1 for getting the answer. Again, 2 marks for setting the equation up, and 1 mark for the answer. And you're also allowed to accept the surd here. So you could have left it as 24 root 3. So, or even written it as 42. That's also okay. So any questions on this? We will finish with this next time. I'm going to give you inclined plane questions, which are slightly more complicated. But the good thing is once you've done them, then you are pretty much prepared for year 13. This is all year 13 material. Excuse me. I'm going to show them to you just a second. They involve friction. So this was a string problem, but that's the same. Now we have 2 kinds of inclined plane questions. There's the ones which we call smooth inclined planes. Now those are not going to be difficult, but they're extremely rare. I think it's since the 2000s, there's only ever been one smooth inclined plane. So the vast majority of them, more than 80% of them, are actually rough inclined planes that involve friction. So you'll find many of them that are all rough with friction because the question is slightly more difficult. But I'll show you how to do that next time. And it's just a little adding on into what. Now, this is typically all year 13's material when you're dealing with friction and rough inclined planes. It's all year 13. But I think it is a good time to do it because the concepts involving resolving forces are all the same. It just doesn't make sense to go and do them 1 year later. So, but that's what we'll do next time, and then we'll move on to Newton's laws of motion. All right. Any questions?
No, sir.
No.
All right. Then I'll wish you all a good evening. We'll meet again on Friday.
You
Okay.
too, sir. Thank you.
Bye.
Bye.